Hello, this is the first lecture of the course on communication electronics. Before we get into the electronics itself, we have to see what are the tasks that are going to be performed by the electronics. And the first thing we have to deal with today is the range and capacity of our links. Now here I'm only talking about electrical links. We may also have ultrasonic links for communication, for underwater communication. We have maybe other physical waves, other physical effects that uh, uh, can be used for communication. But today we are only going to look at electrical and optical devices, where optical devices are an extension of electrical devices. So the first thing we have to see is how do we achieve capacity. Our user is going to ask us how many kilobytes or megabytes per second are you able to transfer. And to do that, we have to first to see the theory. Theory was quite confused for many years, maybe only 100 years after the first telegraph communications, the first wired communication, cable communications. Claude Shannon, shortly after the Second World War, came up with a theorem to treat all different communication, all different information that can be sent out over this communication link in the same way. So here I assume the most simple optical communication. I immediately have to say that this is optical communication. Very low technology, sending smoke signal by having a fire on a mountaintop, so these smoke signals are well visible from the valley. And they can cover quite a large distance here, maybe a few kilometers. And with the smoke signals, we have all the problems of any wireless communication. So we have clouds of smoke, but these clouds of smoke can only repeat at a certain period t here, because if we generate clouds too quickly, if the clouds repeat too quickly, then all these small clouds of smoke will merge into a single cloud and no information can be transferred any longer over this link. Also, the clouds have to be large enough to be visible from the valley. So we have one constraint, that clouds are large enough, and they should not repeat too frequently in order to be able to separate the single smoke signals. We also have interference in this link. We have an interference, when interference I call noise here, so that's the suffix n here. Noise in the form of natural clouds. Natural clouds will interfere with our transmission of smoke signals. If you are not really in the desert, in the very dry desert with no clouds at all. So Claude Shannon came up with the theorem that states how much information can we transfer over such a link, given the energy we put into the clouds, so the amount of wood we have to light this fire here, the amount of wood that's needed to light this fire here on the hilltop, and this is the signal energy, and the noise energy or interference energy we have in the denominator. So the important parameter here is the ratio of these two values. And this is the formula. The information I has the unit of measurement symbols. How many symbols do we have? So this is the information of how many symbols can we transform with one such signal. And the symbols have a certain alphabet size if we are just using text. it will have 26 English text will have 26 different letters. We may transmit decimal digits. So we have 10 different symbols. The size of the alphabet is 10 here for using decimal digits. What is very popular today? Binary digits or abbreviated bits where m is just equal to 2. Claude Shannon made all his proofs using m as the base of the natural algorithm, so 2.718 and so on. So this is quite difficult to understand, but proofs are easier made if this is a natural logarithm here. And what Shannon actually did is he proved that this, he did not prove this equation directly, but he proved that if we have less energy than required, then we cannot transfer information. And if we have more energy than required, then we can transfer the required information here. Of course, to do this efficiently, we need some coding here. And Shannon didn't tell us how to make this coding. So his theorem is very important, but we don't know how to make the coding. Coding is still an open issue. Many codes have been developed over the years, starting with the very first telegraph code made by Samuel Morse more than 150 years ago. So what kind of coding shall we use to make best use of our link here? The amount of information itself is not what people are asking us, because usually in a link we are trying to transfer some information, a certain amount of information, in a defined amount of time. So what we actually need here, here should be signal energy, not symbol energy. Signal energy I should have written here. Here we should have signal energy, not symbol energy. Usually it's one symbol per signal, so that's the reason why I make this mistake here. If we look now at the capacity is the amount of information to be transferred in a certain amount of time. So it's the derivative of information over time. And if we make this derivative, we simply transmit one signal per unit of time t. This is the period of the transmission of signals t. Here should also be usually signal period, not symbol period, but we usually transfer one symbol per signal. This is in seconds or in another time unit, say in hand sent Morse telegraphy, and usually this is calculated in words per minute. So there may be also information given in words, time given in minutes. Usually we have seconds here. And we simply divide this equation we had before with the period t. We transfer one signal in one period t. According to the Nyquist theorem, the bandwidth of such a signal, bandwidth b, that's given in hertz, is just 1 over 2t. 2t because the bandwidth is 1/2 of the inverse of the period of the signal, according to the Nyquist theorem. And if we insert this quantity in the capacity equation, we see that the capacity is bandwidth times logarithm of 1 plus signal to noise ratio. Signal to noise ratio can be expressed in energies. Exactly the same thing can be expressed in powers, because we think that we assume that our transmitter has a constant power here, a constant amount of wood used to light up this fire, and we can also express the same capacity in powers, which is much more practical than energies. well, depending on the application, whether we are talking about energies or about powers, in watts. So energies was measured in joules here, this or watt seconds. Power is measured in watts. In any case, we could use any reasonable unit for power, because we are also always dealing with the ratio, and we should use the same unit of measurement both for the signal power and for the noise power. So if we go to our most frequent case, we transmit binary digits. If we transmit binary digits, then we have here the logarithm on the base of 2. Logarithm with a base of 2 for having the capacity in bits per second. And it doesn't matter here really whether we are having a digital transmission, transmitting symbols, letters, digits, or we have an analog transmission. This formula also applies for an analog transmission as well, because we could compute the capacity also for an analog transmission, the required signal to noise ratio, the required bandwidth we have. Now the noise we have here, even in the case of smoke signals, the noise power is usually evenly distributed across the frequency spectrum. So noise power is simply bandwidth times noise spectral density. This is a very simple relationship if it's distributed evenly across the spectrum. If the noise spectral density is constant, a constant is not a function of frequency. We shall see later that the noise spectral density may be a very slow function of frequency, but this does not affect our calculations. The noise spectral density, again, watts of power divided by hertz of bandwidth. It's again joules. So noise spectral density is again in linear units. It's expressed in joules. And if we put this noise power into our equation, we see that the capacity, actually bandwidth, is here represented 2 times in this equation. First it's multiplied, then here it is divided by bandwidth. So this capacity is not going to be a simple function of bandwidth if the noise spectral density is constant for a particular. Of course, capacity is always proportional to the power we have available, yet it is proportional to the power, but it is a logarithm in between. So if we increase the power, the capacity does not increase that fast. The capacity of the link increases slower than the power itself is increasing. If we look at this noise spectral density, and if we look at electrical, electronic, and optical communications, the natural noise that's always present, even if our electronics were perfect, even if it did not add any noise to the system, there is always some natural noise. At low frequencies, so I'm talking below 100 gigahertz, we call this electronics or radio. Frequency is denoted by the symbol F. Here the noise power is constant according to the Rayleigh-Jeans approximation, and the noise spectral density is simply the Boltzmann constant times the temperature, the noise temperature. Noise temperature at 20 degrees centigrade is 293 Kelvin. So about 300 Kelvin here. So we see how much noise spectral density we have, and if we know the bandwidth, we do also know how much noise power comes here. The Boltzmann constant that plays a role in this equation. This was before 2019, this was a measured constant. 2019 we have a new definition of international units, and the Boltzmann constant is actually no longer measured, but it's defined to define the Kelvin. Kelvin is the degree Kelvin is the unit for temperature. So Kelvin is defined through the selection of the Boltzmann constant, and this is now a fixed number. Here should be identical, not approximately, but this is now identical. Here, no longer approximate. Approximate was before 2019. Now this is identical, like here. In the optics, the noise is different. Here at low frequencies we had thermal noise, so this is black body radiation, and Rayleigh-Jeans approximation gives us this simple formula here. At higher frequencies in optics, and also if you go further, ultraviolet, X-rays, gamma rays, we have the problem that the photons become pretty heavy. Each photon carries lots of energy, and there is just a small number of photons. The signal is actually composed out of a small number of photons. Here in the radio region, we have huge number of photons, and the signal is practically a continuous signal. So this is like a liquid, our signal here. Here at in optics, our signal may be in the light. In the visible light, this is sand, and this becomes gravel in the ultraviolet, and this becomes stones in the gamma ray region. So we have lots of noise because our signal is not continuous, and we call this shot noise. I prefer not to use here the word quantum noise, because quantum noise, all noise always comes from quantum effects, so I prefer not to use the word quantum. This noise is given by the Planck constant. The Planck constant gives actually the energy of a photon, and this Planck constant times frequency. At optical frequencies we use the Greek letter ni for the frequency. It's just a convention. So this is the photon energy. The photon energy times the bandwidth, as long as the bandwidth is much smaller than the frequency, because this is not a constant of frequency. But over the narrow bandwidths we use, we can assume that this thing is constant. Also, the Planck constant was a measured constant until 2019, and now the Planck constant today, the Planck constant is a selected constant to define the kilogram. The kilogram up to 2019 was defined by the standard weight made from special alloys and stored under vacuum in Paris at the BIPM, Bureau International of Poids et Mesures. So this kilogram in Paris is no longer important because we have this definition through the selection of the Planck constant. So Planck constant and Boltzmann constant now are selected constants that define the Kelvin and that define the kilogram in our system of measure. This is after 2019, the convention of 2019. What we see is that in the near infrared, 1.3 micrometers is the typical wavelength in free space used for optical communication. We have quite much more noise than in the electronics radio range. So this noise is actually higher already in the near infrared visible range, and it's much larger if we go here to ultraviolet, to X-rays, to gamma rays, to cosmic rays. So it's probably not worth much going too much here, because we get too much of this shot noise. Still, as soon as we get the noise spectral density, As soon as we have it, we can make this simple calculation. In optics, we have to care about that this bandwidth is not too large, so that we can assume that n0 is a constant. Here, in between the two regions of thermal noise and shot noise, we do not have the total curve. This is green curve here, does not actually fall below this value or this value. Noise never goes down. Noise always stays. There is no advantage of using this particular frequency range in between here, because noise never goes down. Yes, the white noise, the black body radiation, according to the Wien law, decreases with frequency, and the complete Planck law or black body radiation also decreases. But it's overtaken here by the shot noise. So the sum of the two noises is always larger than the white noise in the low frequency range, radio electronics, and the shot noise in the optical range. So there is no particular range of using this frequency range, say, to get lower noise. We should take care when comparing different texts that frequency may be written as f in electronics, as ni in optics. We usually talk about optics being above 30 terahertz. We talk about radio being below 100 gigahertz. This selection makes sense. Why? Because the atmosphere in between here is almost opaque. So there is no transmission in the atmosphere of Earth in this region. There is yet another problem. Hardware for this frequency range between 100 gigahertz and 30 terahertz is very difficult to build, is very difficult to use. In optics, we have components that deal with optics, like photodiodes, like lasers. In electronics radio, we have transistors of many different kinds, semiconductors. But in here between, this is difficult. Today, maybe the maximum frequency transistors can achieve is about 1 terahertz. So we could get up here to 1 terahertz with today's electronics, but the Earth's atmosphere is almost opaque here. So free space transmission in the Earth's atmosphere is no longer feasible. We could do this in vacuum of free space, and optics, on the other hand, going down here, even at 30 terahertz, detectors for 30 terahertz require cooling, cryogenic cooling at very low temperatures. So even here, photodiodes, photoresistors, photodetectors are not very practical. Only when we get to about 10 times higher frequencies, photodiodes, detectors can work at room temperature here. Photodiode for 1.3 micron can work at room temperature. So only here we can have simple hardware to use. The same way with transistors. Transistors up to 100 gigahertz are maybe today conventional components. Up to 1 terahertz, going 10 times more, we can no longer have connections. We no longer can make electrical connections. Coaxial connectors are maximum available up to 110 gigahertz, the W connector, or 1 millimeter connector. We have to use waveguides. We should build our antennas themselves on the chip that carries the transistors. So the antennas should be integrated in the chip, and these antennas may be put in waveguides, but even waveguides at already 100 gigahertz have a huge loss. At 100 gigahertz, a copper waveguide has a loss of 5 dB per meter, so this is not really practical what we can do here. So this is talking about noise. I'm not dealing here other methods of communication because, for instance, underwater ultrasonic noise for underwater communications is yet another thing to talk about. Here I didn't say anything on this graph about the attenuation. I only said that in this region here, the attenuation in the Earth's atmosphere is very high. In free space, it's not a problem. With radio, we have the atmosphere transmitted. We have several windows in optics when we can make communication, free space communication. In electronics radio, we can use copper conductors, coaxial cables. Here, in optics, we have optical fibers, not for any wavelength, but for some particular wavelengths. Optical fibers are very efficient here. Now, if we look at the Shannon's theorem, so the Shannon capacity for a link, we have to play around with the power we have and with the bandwidth we have. Both power and bandwidth are expensive. If we go back to this, so here power and bandwidth are both expensive. Power is expensive in the terms of firewood we need here on the mountaintop to light our power, and is expensive in terms of batteries if our device is powered by batteries. It is very expensive in terms of heat that is produced. Usually today it's easier to power is relatively easy to generate with an electronic circuit, but due to the finite efficiency of an electronic circuit, this power generates also heat. Such a transmitter generates heat, and it's very difficult to get rid of that heat. So it's batteries, either rechargeable batteries in our mobile phone, either solar batteries on the communication satellites. Power is expensive here. The other thing that is expensive is bandwidth. Everyone wants to make communication, so bandwidth, if it's our own cable, the cable has limited bandwidth. If we need more bandwidth, we have to install a second cable. If it's free space communication, our communication may cause interference to some other user. So if we want to use a chunk of radio frequency spectrum, we have to register our transmitter to the relevant authority, and we have to pay a certain amount of money to use this spectrum. So this is real money here, this bandwidth here. Especially if you think now about the new mobile communications and the amount of money companies, service providers are prepared to pay for the bandwidth. So bandwidth is expensive, both are expensive, and now we have to see what can we do about with bandwidth and power. And the first thing we can try is the very long reach communication. Say we are sending a space probe up to another planet. Here probably the cost of the mission, say to fly to another planet, is very high, and we are not concerned about the cost of the bandwidth. We are just concerned about the cost of the power, since this space probe, this interplanetary space probe, has a very limited source of power, usually a radioisotope thermoelectric generator, and we have a very limited amount of power to power our transmitter. What can we do if we increase the bandwidth? If we increase the bandwidth, you see bandwidth plays a role here, it's multiplied, and here is divided, so it's a question whether the capacity will increase or decrease, increasing the bandwidth, or stay constant. Well, in fact, this bandwidth that's in the denominator of the fraction here plays a smaller role than the bandwidth in front, because this is under the logarithm, and the capacity actually increases. If we increase the bandwidth. So if we increase the bandwidth far beyond what required for a single bit per for the transmission of a single bit per symbol, far wider bandwidth we use, and it's convenient to increase the bandwidth because the mission is so expensive, the power is so expensive, we try to increase the bandwidth. what we see is that the bandwidth, the capacity of such a link, reaches a limit here. If we go with the bandwidth even to infinity, we will encounter a limit. And we can calculate the limit from this equation. That's given by our power. Of course, the capacity is now given by the power. It's given by the noise spectral density. And this logarithm, natural logarithm of 2, comes out of this logarithm with the base 2 up here. So we have a precise limit for the bandwidth. I call this C infinity, so capacity at infinity, and this is a strict theoretical limit. So it does not really make sense to much increase the bandwidth, because here we are very close to this curve. We should not forget that we still have to pay for the spectrum used. We still have to ensure that this spectrum is interference free from other users, and we cannot go with the bandwidth really to infinity, but we can stay here in the safe region when we are already close to the C infinity. Also, increasing the bandwidth increases the complexity of the coding used, so also the decoding becomes a problem here. One practical use of this equation, besides interplanetary space probes, was the UMTS mobile phone system. The UMTS mobile phone system used code division multiple access, and with code division multiple access we actually have much more bandwidth than strictly required, but we have a very poor signal to noise ratio. In fact, with CDMA, code division multiple access, we are up here already by the system definition. There were special coding protocols developed just for UMTS, and they are now forgotten because code division multiple access is not particularly efficient if we consider both power and bandwidth, especially if we consider capacity here, how much capacity we get out of it. The other possible limitation is we have to pay for the spectrum. So bandwidth is constant. We see what can we get if we increase the power. Here, rewriting the equation is this way, so bandwidth is constant. We vary here the power of our signal. The capacity is shows a monotonic increase of capacity if we increase the power. So the power, actually it's convenient to increase the power if we can do so. But this is in this way we can also increase the spectral efficiency. So if we divide the capacity with the bandwidth, so this spectral efficiency C over B, it has units just bits, because bits per second and hertz actually cancel out. These two actually cancel out. So spectral efficiency is now a new term, a term coined when spectrum became expensive. So we are talking about spectrum efficiency, how well can we use our spectrum. It seems that this spectral efficiency could go to infinity if we raise here the power to infinity. Spectral efficiency goes to infinity. But this in practice, this is not the case. In practice, we also have interference. Interference here, this is no longer noise. This is interference that we may cause it and other users also can cause it. So interference, the power of interference, that adds up to the power of noise here in the denominator of the Shannon equation. It's actually linear distortion, that's multipath. This happens both in wired and in wireless links. It's non-linear distortion. Non-linear distortion that may be caused by the non-linear devices, transistors in our transmitter, may be caused by a non-linear transmission medium like the optical fiber. And both these are exactly proportional to our signal power. So if we increase the signal power here, we cannot make things better. The nonlinear distortion only gets worse. And finally, we have the power of crosstalk. So other people are also using the same chunk of spectrum, the same B, and they cause interference to our communication. And this also, if we increase the power, other people can also increase their power. So the ratio of our signal to the crosstalk remains constant. So again, here we come up to a practical limit with interference, and this practical interference limit gives us a spectral limit for the spectral efficiency, a practical limit of about 10 bits. This may be 10 bits per second per hertz. So 10 bits, this is a practical limit for just one twisted pair in our cable, or one coaxial cable, or one polarization or one transmission mode on our radio link. So if we have more cables in parallel, we can increase this limit. If we have more modes of transmission over our radio link, we can also increase this spectral efficiency here. This is also a thing that will be discussed later on when we come to wired and wireless links next hour, when we're going to discuss this thing. So this is a short introduction to the Shannon Theorem and what we are talking all about. We have to provide our users with a certain capacity. And our users really don't mind how do we transmit this capacity, how do we achieve this capacity. They only just want capacity. They want to watch the movie from YouTube. That's what our users want. They are not interested how the technology works here. We have to care about the technology, and of course the Shannon Theorem will tell us what to do in our communication electronics, what kind of processing we need in our communication electronics to do that. I intend to finish this hour with a simple, very simple, easy to understand example of how to use the Shannon formula. My example is an analog telephone line modem for computer communication. This maybe today it's no longer popular, it's obsolete, but it was very popular 20 or 30 years ago for the first internet access. So in a telephone line, analog telephone line, the speech frequency band extends from 300 Hz to 3400 Hz. This is the standard speech frequency band defined by the ITU, and the telephone line only supports this frequency band. On the lower end, there may be in-between transformers that would add attenuation at lower frequencies. At higher frequencies, we may have filters in the line that will actually limit this upper frequency end. So from the line point of view, if it's an analog line, if this signal gets digitized in front of the A to D converter, there is a band pass filter that only lets pass this band from 300 Hz to 3400 Hz. So we already have both a high pass filter for the lower end and a low pass filter for the higher end. So the bandwidth that's available is 3100 Hz on an analog telephone line. Again, if we are talking about the telephone, the analog telephone, the guaranteed signal to noise ratio is only about 35 dB. 35 dB transformed into linear units, it's 3162. And this is again a fixed limit. If we have a digital telephone exchange, there you have filters and A to D converters, and this is actually the figure defined by the A to D converter in the telephone exchange. This actually may be worse if you get analog noise in the telephone line, which frequently happens. So if we apply the Shannon theorem here to compute the capacity of such a link, it's b times logarithm with the base of 2 to get the results in bits per second. Here we put in our signal to noise ratio in linear units. So we have to compute the logarithm of base of 2, we usually have the natural logarithm divided by the natural logarithm of 2. So the definition of the logarithm base 2, we have to divide these two logarithms if we do this on our calculator, because calculators don't have natural logarithms on the base of 2. On the other hand, if we are doing this on a computer, there are very efficient algorithms to compute the logarithm on the base of 2. So in the binary world, it's a world on its own. And maybe this logarithm is easier to compute than this one. Forget the Taylor series from mathematics. That's a very inefficient algorithm. There are much more efficient logarithms in the binary world here. If you compute, if I put this figure here, if I put this figure here, I obtain a theoretical maximum capacity of a telephone of 36 kilobits per second. Yes, this is the theoretical figure. You cannot get more than this, thinking about considering these limitations we have here, bandwidth and signal to noise ratio. We cannot get better than this. Yet, if you may remember, 20 or 30 years ago, there were several 56 kilobits modems on the market. How did they obtain 56 kilobits if the theoretical limit is 36 kilobits? I really don't know this. So this is actually our limit, a practical application of the Shannon's equation. We see that we cannot really do much over an analog telephone line, considering the limits it has. Of course, if we are using a wider frequency band, like in an ADSL modem, then we can get much more than 36 kilobits per second. But the bandwidth is larger. That bandwidth will not go through the filters in the telephone exchange, will not go through transformers, will not go through the A to D converters, will not go even if we have some poop-in coils to reduce the attenuation of our line. Will be limited there. So ADSL modem can achieve much more, but if we have a relatively short and dedicated twisted pair just to our communication. This is my short introduction to the Shannon theorem, and we are going to use it everywhere in our calculation of links. And finally, in the electronics, we are talking about communication electronics. What electronics do we need to make best use of the theory of the Shannon theorem here, considering that we are usually talking about capacity. We are usually using bits, so and we are considering spectral noise density, where on this graph here we only have natural sources of noise, but our electronics can get pretty close to this limit. So we will have to when talking about the electronics we will be also talking about how much noise does the electronics add to these signals here. So we're going to talk about that. This will be a consideration. This is just the natural limit. We should understand that we have a natural limit. Electronics will add some noise, but not really that much noise. Today the electronics is pretty good, and we can get quite close to these limits we have here. So next hour, from this first talk, we are going to have a look at both wired and wireless links. How do they behave? What range and capacity can they achieve? Not really capacity. I'm going to talk about bandwidth, and range and bandwidth we can have, and the capacity is of course provided we can have enough power. Enough power reaches our receiver. So range will be attenuation that we are going to talk next hour. So this is for this hour.